Hi everyone, welcome to Structures 2. I know most of you were part of Structures 1. There are a few people who are in the advanced placement program, and you guys have missed out on the opportunity to take Structures 1. So for you, we're going to do a very in-depth review lecture next week. And for everyone, it's nice to kind of get a freshening up of what you learned last year, because this is a new version of the program, and you guys are the first students to kind of have this year-long gap between Structures 1 and Structures 2. Previously, Structures 1 was in the fall, and it ran through to Structures 2 being in the winter term. So I'm going to take a few minutes, introduce myself, and then I'm going to go through a relatively basic, kind of easy lecture. And for those of you who did Structures 1, you're going to recognize this lecture because it is literally the exact lecture we did as the first lecture of Structures 1. And I think it is so important to review this lecture. As I told you all at the beginning of Structures 1, everything you need to know about structures, you already know. I throw a whole bunch of numbers and information at you that makes you start to doubt yourself. And then towards the end, you start to be able to put it back together. The reason I like to do this lecture again in the middle of kind of your structures knowledge is to remind you that still, everything you need to know about structures, you actually already know, or you have a really good intuitive sense for it. So I'll go through my little intro, introduce myself, and then we'll kind of lay out the course, what's going to be expected of everyone, and then we'll jump into strength, stiffness, and stability. So I'm Shannon Hilchey. I am a structural engineer, practicing structural engineer, and I've been practicing for, I'm looking at my stuff on the wall, almost 20 years. So I think next year it'll be 20 years. So I worked at Blackwell Engineering for several years. And then my husband is Dave Bowick, who's the owner of Blackwell Engineering, one of the owners of Blackwell Engineering. He's since brought on partners. When we decided to move in together, I figured it was smart for me to work somewhere else. So I did a little bit of a switch up for a while, and I joined Cast Connects. Now, technically, my role was technical sales, but I got to do a lot more than selling. It was a really kind of cool opportunity to meet with some of the top architects and engineers in North America and work with kind of I want to say a new product, but it's basically creating things out of steel in a way you might not normally do. So that was really wonderful. But I very much missed doing engineering design. So I decided to open my own firm. So just as I was getting going, I had been working at my company, the company I founded, for 4 or 5 months when U of T called me up and they said, "Hey, would you teach our structures program?" And so that fall I started teaching the structures curriculum, and here we are, I guess almost 8 years later. So my company, Fat Lab, focuses on high-end installations. Now, what does that mean? It could be a canopy, a guardrail, art. I do a lot of art installations. And so what I do is I provide the engineering services for these things that normally aren't in a base building engineer's contract. So feature stairs aren't part of the base building engineering contract, and they often get designed by the fabricator, which is fine, except the architect might not get the vision that they want. All of a sudden, the person designing it or doing the engineering is doing it on the behalf of the person who wants to make the most money on the stair as possible. That's not a slight to fabricators. We're all trying to make the most money that we possibly can. But the motive for me is to do it in the interest of the architect or the owner. So I come in and provide engineered solutions to what would normally be kind of offloaded into the fabricator department. The really interesting thing is I get to work with architects when they're at their happiest. Their heart and soul is in these little feature elements, and I really get to help them get realized on these projects, which is really fun. And sometimes I do whole projects. I usually don't set out to do whole projects with my firm, but I've had some kind of unique opportunities where it was hard to say no. I was kind of taken along for the ride, a wonderful ride on some really cool projects. One of them I've added to my kind of slideshow here, and one of them should be coming up. It's under construction. My scope's complete now, so hopefully pretty soon the building will be enclosed and we'll start seeing some cool pictures of it. So what makes me qualified to teach this course? Well, I have, through my time at Blackwell and through my own firm, I've been really lucky in the projects I've gotten to work on. I was very fortunate to get hired at Blackwell right at a university. And since then, I've gotten to just have some unique opportunities. So this was a project I did very early in my career. I wasn't the project lead on it for Blackwell, but it was kind of one of the first projects where I did all of the engineering work on it. So this was the Canadian Peace Bridge Customs Plaza. And this is before we had really cool 3D modeling software. There was modeling software, and I'm talking not just about graphics, but also the engineering side of it. So there's kind of two components to our models. There's the engineering component, and there's the visual kind of presenting of information side of it. This was done in 2D drawings to represent this project, and I had to create out of what was linear software analysis programs. So for the actual engineering, I had to create a way to do this in 3D. The way to input it was not easy, and for every sloped line, I actually had to use a spreadsheet to derive the X, Y, and Z components of the element to be able to input it into my modeling software. So I didn't draw these, I entered all of these components as nodes to draw lines in between them. So this would have taken me probably, I would say 3 weeks to build the base of this model now, and it took months to do it back then. So, a really unique kind of situation. NCFS headquarters, if Doors Open Toronto allows access to buildings this year, take the opportunity to walk through this building. It is absolutely stunning. It is the Native Child and Family Services headquarters. So this is an institution run by Indigenous people for Indigenous people, focused on the well-being of children and family within the Indigenous community in our district. So they have places around Ontario that I know of, but maybe it's even national. And so this is a really lovely building. They really did it with focus, and Levitt Goodman is fantastic at dealing with kind of Indigenous, bringing in Indigenous design features, and kind of working with Indigenous designers to help realize these projects. And they came to us, and so this was probably 2007, 2008. They said, we want a modern representation of a Native longhouse. And so we went away and we said, okay. And Dave and I had been playing with reciprocal frames, and we were really looking for an opportunity to use reciprocal frames. And reciprocal frames use small elements in a repeating pattern, and it's not stable until it's all in. It has a lot of benefits. It's not the easiest way to build something, but it was common practice kind of in when we didn't have long members to build with. And you see a lot of reciprocal frame style techniques in Indigenous structures, older Indigenous structures. And also it has a representation of basket weaving, or that kind of very primal look of weaving things together. So we were very excited to use the opportunity to create this structure. And so within this other beautiful building, there's a very small building that we were very fortunate to be allowed to work on. So this is the Sisters of St. Joseph, which is another really amazing building with Shim Sutcliffe. I wasn't the project engineer for this, but the project engineer said, we hadn't included this in our scope and now we're in a crunch. Could you look after it for us? And this is while I was still at Blackwell. So I took over the scope of the canopy. And I love this image because I say everything you need to know about structures you already know. You intuitively know looking at this that this is unusual. In fact, your gut tells you this shouldn't be possible because it is unique. There was a lot of engineering put into this, and some of it is about how you read the structure and really brilliant detailing on Howard Sutcliffe's part to make it read even thinner and more extraordinary than it is. But you intuitively understand that this long piece here should normally have a post here. You know that this is a long cantilever. And you know that this looks like a very short backspan. Because really what we have is a support here and a support here. And you intuitively know that this looks unusual. So what I need to teach you is how to make the usual work in this course. That's the idea, is we have to understand the usual. And then when you get into the unusual, you'll have the usual as a building base to help you proceed. So for those of you that have done any course in the any courses within the landscape department at Daniels, you'll probably recognize North Design Studio. So this was one of their projects, I think way back in 2008. I'm really bad at updating my website as a single person firm. The fees for the photography is almost equivalent to my fee for the engineering services. So I usually can't afford the photography for photos. So these all came either through the benevolence of the architect, as long as I make sure I give all appropriate credit, or from Blackwell projects. So this was a really lovely kind of opportunity to work on. Originally, these were all rounded elements, and I, as I said, back then had to model as straight line elements. And when I showed them my analysis model, Peter was really excited, and they really liked that kind of fractured look to it and incorporated it into the design. So that was pretty exciting for me to feel like I had some small part in reading in their beautiful work. So this was one of the first projects that I took on as Fat Lab. I was still working in conjunction with Blackwell, but this really kind of helped launch my firm. So the concrete building was being designed by ARC. And normally in a building, you build the concrete building, and then the wall suppliers would come in, measure everything, go back to their plant, build the wall panels, come in and install them. And then the window suppliers would come in, measure all the openings, go back to their plant, fabricate the windows, come back and install them. This project was unique for several reasons. One, we were trying to build everything on a curved surface that had 8 distinct radii, and all of the wall surface was built out of triangles that weren't in a single plane. So forget the fact that it's on a curved surface. They actually weren't flat. So they were all skewed relative to each other. A mathematician was hired to generate the patterning using only 3 triangles in, I believe he had worked it out to 8 or 9 separate conjunctions of those triangles in a repeating pattern that would not be representative by the human eye. So it would be hard to pick out those patterns. Also, separate materials were used on all of the triangles. The biggest problem was that the window components, which were made up of multiple triangles, were out 500 millimeters from the concrete, but not always 500 millimeters. It varied anywhere between 350 and 500 millimeters from the surface of the concrete perimeter. We also had the issue that while the concrete was being poured, they had such a tight timeline, they needed the wall panels to be being fabricated and the windows to be being fabricated. So I was brought in to A, find a structural solution to support these windows, and B, come up with a modeling technique that would also be able to work out my engineered solution and be provided to the steel supplier to make these steel insert panels and the window supplier to be able to fabricate their window panels without coming to the site to make any measurements. We had one call from site with a problem, and it was actually at this point right here, and I got a call from site saying these things don't line up, there's a major problem, come to site. And Dave and I said, okay, well, we're on our way to the airport, can we stop in and see you on our way to the airport? And some of you have probably heard this story before. And so we showed up, we showed them that this part of it was not what mattered, but this line, this surface right at the perimeter of the window. And so we held a ruler up to this point out here. What happened right here was irrelevant. What happened out here was we held a flat ruler up to it. Everybody calmed down. And then I said, okay, we have to go catch a plane. My wedding dress is in the car. We're going to get married tomorrow morning. So off we went and got married. We didn't get a single call from site after that. So everything got installed without a hitch. Hitch, we got married. This I like to show. This is what I was working on right while I left Blackwell. So I stayed on for a while, even while I was with Cast Connects, kind of working as a consultant on this because it was such a flagship project. If you've had the opportunity to go to the gym in last term or even the year before, this is the Varsity Centre for High Performance Sports. It spans, this building does not touch down here at the ground. It is supported here, and it is supported here, and it is a 54-meter clear span over a field house or a gym below grade. So there was all kinds of reasons to do this, but a really unique kind of building structure. This is a cute little project that's just completed this year. It's the Thompson Park Pavilion by DTAH. And again, intuitively, you know that is a long cantilever for something that is so shallow. And so there was kind of a lot of work and effort put into making this very slim roof profile on this building. And you can see down here, there's another cantilever at this end. It's kind of, this is the lesser of the two cantilevers. So if you get the opportunity to go for a walk on the Leslie Spit, this is a great place to go, and you'll pass this building on your way into the park. So let's go through kind of what this lecture is going to be. First, we're going to talk about what the expectations are for this course. Then we're going to go through strength, stiffness, stability, and then I always end the lecture with takeaway tips. I woke up on Monday morning in a bit of a panic, realizing I had forgotten to make a change to the syllabus that I kind of left in the structure of the course, specifically for this year. In previous years when teaching was in person, there was almost always a reason at least one class got canceled. So as much as it's a 12-week program, I always made all of the material fit in 11 weeks. Last year, being online, there was no reason to miss a single course. I kept one lecture free, because remember, they were the last class to go through sequentially throughout the year. So they started Structures 1 in the fall and did Structures 2 in the winter term. I left that one lecture free because what I've done for you for this term is next week is that lecture. So we're having 12 full lecture sessions, and next week I'm going to go through fully worked out problems that would have been able to be completed by the end of Structures 1 last year. So for those of you that want it as a refresher, that's great. For any of you that are in advanced placement, I understand that some of you don't need to qualify for the fact that you aren't doing Structures 1. It's a little bit bonkers to me, and so you guys might struggle a little bit. There's not much I can do about it. I've included this lecture next week's lecture explicitly for you. Those problems are already posted in this week's module, so you can start looking at them and getting your head around them. If you need to, you can try to arrange something with a tutor. We could try to reach out to one of your TAs. you guys have a unique opportunity this year that one of your TAs is actually a structural engineer. They might be able to reach out to colleagues if you wanted to hire kind of another engineering student to help you out on some of these problems. So that will be next week. So let's go through what the kind of makeup of this course is. Let me drink my coffee. Okay. So the three components for the marking is assignments, exam, and project. Your assignments are worth 30%, and there are 10 assignments, and that means each assignment is worth 3%. That is not nothing. The assignments are they're harder than the exam would be, I believe. I try purposely to make them harder than the exam questions so that you've done the hardest thing possible during the assignment, and then the exam maybe is a step back from that a little bit. The assignments will be found on Quercus the day of class, so Thursdays assignments go live. They're available for 1 week. You can submit it at any time you like, but you can open it and leave it open all week if you want. And if not, it will auto-submit at 11:59 p.m. on Wednesdays. I will, a day or two after the lecture, I will post the answer sheet so you can go through and work through the problems. This year, the way the timing works between the class posting and the tutorial time slot means that you have the opportunity to talk to your TAs before the assignment is due, and maybe have had an opportunity to really get your head into it. Your TAs are going to be running online tutorial time slots. That was kind of demanded by we'll get into the tutorials in a minute. So if you need to, try to arrange prior to the due date for any extensions that you need. I am very, very nice if you are very, very nice to me and come to me and kind of give a heads up on what's going on. You don't even have to get into specifics. My philosophy is everyone has a problem where, dog ate your homework, you got sick, whatever. And so no questions asked. I will usually allow someone an extension on an assignment. As long as I see that you're kind of diligently trying throughout the term, I will often kind of no questions asked help out on something to give an extension as it's required. The project's due the last day of the semester. That's been set by the director of the program. I used to have it on the last day of class, but that fell too tightly within studio, especially where you guys are tied to comprehensive studio. So we determined that, mine could be the last thing that's done. Maybe you can take a breather, relax, and just focus on that. There's 2 parts to it. The first one is done in pairs to match your studio project. The arrangements are outlined for people that don't have a studio partner in this class, or for some reason doing it solo. So there is something listed within the project outline, which will be posted later. So don't panic if you don't have a partner in this course or if you're solo. And the idea there is that you're going to be creating a set of structural documents for me, but we're not talking fully engineered structural documents. It should be stable. So all of the elements should be stable. As for strength and stiffness, all I'm asking that you do is size it based on sizing guidelines. What you're producing would be a schematic design set of structural drawings. So at a schematic design set, that is typically in the hands of the architect, and you're going to be producing that without the benefit of the engineering. So we'll refresh on sizing guidelines as well throughout the term. And then part 2, I've created another fake building for you guys, and I will I'll assign you specific members on that building that you're going to be doing the complete analysis and design on, which remember means, is it strong enough, is it stiff enough, and is it stable? And for strength, that means are all of the factored loads less than the reduced capacities. So the studio dates have been organized not by me. So So there will be dates where you have meetings with structural engineers. There is an opportunity that I will be available as well for questions, kind of through desk crits that are slightly less formal. So we'll try to make use of those for meeting with me. Arrange prior to the due date for anything that you need kind of an extension for, but remember that is a hard line date for the submittal. I have to provide marks 5 days after the last day of the term, so there's a bit of a time crunch there. Exam. Not everyone gets the exact same questions, but I've pooled slight modifications of the same question that get put into a pool for people, so the difficulty is fair. Very similar to the assignments, there'll be multiple choice, fill in the blank, math, matching. For matching questions, I try to be very aware of anyone with dyslexia or reading problems, and I try to make it very visual on how you can match them without messing it up. Like I don't label things A, B, C, D, E and match them with 1, 2, 3, 4, 5. I find that's really easy to kind of get backwards a little bit. Obviously, it's going to be open book. I will provide the PDF appendix on Quercus prior to the exam. There's lots of downloads, but I don't want you to have to print everything out. That seems a bit ridiculous. And so what I do, if you are going to print something, I recommend it be that appendix, because it's going to take the key elements from each of those PDFs that you will need to complete the exam. It doesn't mean that's all you'll need, but it will be the major things that you need. It'll be almost everything. You should be able to complete 90% of the exam with that PDF. Oops. So the classes. I post the PowerPoint and the link to all the videos on Quercus. The first slide will outline the lecture and the learning points. The last slide will be the important items that I think you should take away from that day's lecture. The PowerPoint and video will be posted by Thursday each week. My goal is always by noon. Today might be a tiny little bit late, and I'll address that again in just a second. The tutorials, the assignment answers will be available the day after the assignment due date. Try to submit any questions to the TAs prior to the tutorial. Maybe it gives them a chance to get their head around something. Maybe they have to do a little bit of research to help give you your answers. So I want you to remember that there's only one of me, and I think there's like over 90 of you this term. Plus I'm teaching Structures 1 at the same time. So start with TAs. You're going to want to reach out to them, see if they can answer your question. If they can't answer it, I am happy to get involved, but I would ask that you start with them. It doesn't mean I don't want to meet with you, but between the two courses, I have like 180 students, and if I had even a 5-minute email with each student, it pretty much steals all of my productive time to be able to record these lectures and prepare these lectures for you. If you do email me, tell me what class you're in. Where I'm teaching 2 courses, if you say I don't understand assignment 2 question 5, I won't know which one it is because the timeline is the same but different assignments. So those of you who were in Structures 1 will remember I have, last year they were 2 and 4, now they're 3 and 5. And this week they're home. We've just gotten word that they go back next week. I have a hard time believing that will last. And if anyone in our house sneezes, all of us have to stay home for 5 days, which means there will be lots of times where I have my kids home with absolutely no childcare. Last year, I specifically kept my kids home and arranged for childcare 3 days a week so that I would have reliability, so that I could always be able to record these lectures pretty much at a set time without being at the whims of school closures. A lot of people chose to have 5 full weeks of working and then 5 full weeks where they were screwed. I needed to space it out a little bit. But this term, I don't have that luxury of having someone come into my home to help. I do have someone here today. There was an exposure at daycare last week. So even though we never got COVID, we had to quarantine. I am not a fan of the 5 days. We went 8 days, but I do have someone here today so that I can record this lecture. But basically my kids they went to daycare 2 days last week. Otherwise they've been home since the middle of December. This course is tied to Comprehensive Studio. The review days have been organized with structural guests to help move your studio projects forward. Sam was fantastic in taking the time to get the dates out early. It's always a struggle to find people because they never want to commit when they can see their deadline on the horizon. But getting them to commit in December, we were able to lock lots of people in. Now, we tried to overbook specifically because we knew we would have the problem of people with kids home getting sick themselves, that we would have a lot of disruption. But the idea is that everyone is going to be matched with the same engineer throughout the term. There are other days where Dave and I are going to come in and give a bonus lecture. Well, actually, it'll be virtual is my guess. And then on those days where you're partnered with other engineers, I am going to be available to either fill in or go around and talk to people. And there's another 2 days, I believe, where I am going to be available for kind of light desk crits with your studio groups. So we've really worked hard to kind of ramp up my or the engineering component within the Comprehensive Studio. I can't personally meet with every group. It's just not possible. I have in years past tried to do it, and it is 2 marathon days of 10-minute meetings. And I don't know that anyone gets quite as much from it as they would hope. And that was before we had guests coming in. So this I think is really going to help. And as I pointed out, part 1 of the project's tied to comprehensive. So what's my job? To meet the requirements set out for the class lesson plan, meet the needs of the majority of the class. Some of you are going to be very advanced and find this very easy. You can go ahead and kind of look up harder questions that you'd like to solve. I have no problem with that. Some of you are going to find some of the concepts difficult. I try to make the course so that if you complete the assignments and do your project, even if you don't do well on the exam, you can still get a decent mark in this program or in this course. I know exams can be very terrifying, really, for a lot of people. So I try to make it that you can succeed without having to ace the exam. That said, you have to take some responsibility within that. So if you think you're one of those people that's going to struggle, I'll do everything I can. The TAs will do everything they can. But do your assignments, complete that work. You have the opportunity to talk to your peers. I not only am I not against it, I encourage people to talk to each other about the assignments, not exams. Did I say exams? I meant assignments. Talk to each other about the assignments. In the past, you would have been sitting around in the tutorial talking to each other, trying to solve these problems. The assignments might have different numbers, but the method will be the same. So take the opportunity to talk to each other. And my last criteria is to be reasonably available. There's no office for me, so obviously I can't have office hours. But for those who remember from last year, I answer emails quickly, or I try to. There will be the rare time where maybe it takes a day or two for me to get back to you, but usually it is minutes or hours at the most. Because my kids are home, my hours are weird. You might not hear from me during the day, but you might get an email from me at 11 at night or 4 in the morning. Because early in the morning is the time where I often record my lectures. So I try to get up before the kids get up. The TA's job. They have to have a pretty good understanding of the concepts. They have to be reasonably available as well. They're going to be providing a 2-hour time slot of set availability weekly, and that's the tutorial for you guys. And they should be able to respond to emails within a few days. Now, this is actually a slightly unique change. I normally say TAs are not practicing structural engineers. They will not have all the answers. You guys have a unique opportunity here where you have one architecture student who is not an engineer and one engineering student who's working on their PhD, engineering student who is not an architect. So there are pros and cons to both of those situations. The structural engineer is going to know so much that can help you out, but sometimes they might know more than you need to help solve the problem. And so bringing them into the world of the architecture side of it is going to be just as fun for them as it is for you learning about the structure side of it. So there's a real opportunity to connect here. So let's take real advantage of this opportunity we've been given. But remember that they don't know much about architecture, or I'm assuming. Let me know if I'm wrong. But they probably don't have a lot of experience on the architecture side of it. Even a lot of practicing engineers don't have a lot of opportunity working closely with an architect. So this is a really fun opportunity for everyone. And remember though that your TAs aren't tutors. If you require more one-on-one time, please try to get in contact with a tutor. What's your job then? Well, you should watch the lecture videos, you should complete the work that's outlined, and you should study for the exam. As I've said, if you do all the assignments and take the time to really try to figure out the answers and don't just complete it quickly and hit submit, and if you don't understand something, talk to your colleagues, talk to the tutor or to the TAs. If you can do that with the assignment and you commit to your project, you'll still need to do the exam, but you don't need to panic that you're dependent on it for a good mark. Tips. Take notes, but the slides are always available. Because these are online, and I do not believe in taking down the YouTube video. I know a lot of professors are very much, this is only to be shown once, it'll self-destruct after 5 seconds. I don't believe in that. If I say it once, it should be okay to be said multiple times. And so I leave these lectures up on YouTube for as long as you want to go back and watch them. That means that any other lectures I've done since the beginning of this pandemic are also available on YouTube. So you can go back, you can maybe see this same lecture done in past years if that's helpful to you. I love questions that use equations. I love questions that use lists. They lend themselves really well to Quercus questions. And you should try to go through all the calculations I do in the assignments. Listen for my cues. I am very friendly when I say this would make a good exam question. I can guarantee you it will probably be on that exam. Okay. Why is there no textbook? Again, even though we went through this in Structures 1, I get asked this question so often that I really need to address it. I would love there to be a textbook. I was working with the CWC, which is the Canadian Wood Council, to actually develop a textbook for architects for structural works. But they've changed the format. They've taken the work that I wrote and they're turning them into learning modules, basically very similar to my course. So instead of producing a book, they're going to end up producing basically what we're going to be doing over the next few weeks. So we're not going to get that hands-on textbook that I was hoping to get. So why don't we have a textbook? What we need to make a textbook work, or what we go throughout this term, is we use 20 pages from the Hibbler Statics book, 20 pages from the Hibbler Structural Analysis book, about 10 pages from the National Building Code, which is similar to the Ontario Building Code, about 100 pages from the Wood Design Manual, 100 pages from the Steel Construction Handbook, and 100 pages from the Concrete Design Handbook. It would be a fortune for you to have all of these. Most of these publications have allowed me to post and share with you in PDF form the pages that are needed to complete this course. The problem with these ones is not only are they expensive and we only need a few pages of them, they're written for an American audience, which means the codes that they follow don't match our Canadian codes, and they use a lot of imperial units, where we're going to try to stick almost exclusively to metric. The only time we really don't stick to metric is there's a few spots where, if we're talking about residential wood, we're going to use the imperial system because it's still standard to show wood framed construction in imperial units. So everything you need to complete this course, I provide for you. I have created example problems that would have been very similar to that shown in the Hibbler Statics and the Hibbler Structural Analysis book. That said, if you want, go online, Google these, buy them. I don't care. I'm certainly not going to keep you from owning these things. And some of them actually even have published components that are accessible where you could use the problem sets and see how they relate to what we're doing. Again, there are more online resources. One of the great things about structures is at least the majority of the components we're going to be going through haven't changed in 150 years. The components around some material sciences and earthquake design, for example, there are huge advancements that's being made in that. Mass timber design is relatively new in the industry, but the principles that we're following haven't changed in 100 years, which means that a lot of what I'm teaching you here today is available in the words of someone else. So if you find my voice high-pitched and annoying, feel free to look up another source to back up what I'm saying. Maybe you just need to hear it in another voice. It's purposely why I get Dave to give the lecture in your studio course for how to think about structures or how to pick your structural system, simply because you all would have heard my voice so much that I want him to give that lecture so that you can hear some of the same things I'm saying in his voice or a different voice. Don't worry about that. Okay, so why are we doing structures? You guys are architects, you're going to hire an engineer to do all your structural work, and that's true. Except you guys are often picking the materials and doing the layout and making some preliminary drawings that have preliminary sizes on it. And to do all of those things, you have to have an understanding of material limits, and you have to understand the relationship between depth, length, strength, deflection, and that a small change can have a big impact. If you guys remember, when we looked at the moment equation last year, it was W, which is the uniformly distributed load, times L squared divided by 8. So that was a load that was a uniformly distributed load on a simply supported beam. Length was squared, which means increasing the length is not a linear increase in the moment on the beam. So increasing the length has a big impact on the moment. So we want to be very careful about what changes we make to our system, and if we need to fix things, how we can play with those things. So again, these are difficult concepts, and for some people it's difficult math. You need to do the math a few times to understand these concepts. Last term, we were introducing a lot of unique concepts to you guys, things you might not have ever seen at play before. There's going to be some of that this term, but a lot of it is going to be directly from our code books. So we're going to do, for example, when we get into our steel component, we are going to open up this book and flip directly to some pages that have very specific equations on them, and we are going to go through and do those equations. We're going to have to figure out what all the variables are, find the information for those variables, and then complete the math. Some of the equations look straight up bonkers, but we are going to work through them slowly, and we're going to break the math down to easily kind of keep track of it without making mistakes. And I'll try to go through that several times for you. All right, structures 1 versus structures 2. In structures 1, we learned how to create our system. We learned how to do our preliminary design. Remember, that was all of our sizing guidelines or our rules of thumb. For those of you that are just jumping into structures now, our sizing guidelines are posted on Quarkus. You're going to want those. Those are going to be very helpful for preliminary sizing. You will probably use those throughout your career. We figured out what all the loads are that act on a building. We looked at the load path. So how does the snow on the roof travel through the metal deck to the joists, get to the beam and get to the column, and then transfer all the way down to the foundation, and then design the foundation so it gets out into the soil. So how does that snow load up on the roof make its way through the building to come out into the soil below the footing? And then we looked at what the internal element loads are. So we looked at that beam, for example, that was supporting joists that had a metal deck that had the snow load on it. What does that mean is happening internally in that beam? And so we looked at the shear force and we looked at the bending moment within that beam, and we figured out what the worst factored internal loads were for those elements. Remember, factored means we figured out what all the loads were and then combined them and added an extra little bit to make sure that was a reasonable load, but bigger than anything we should ever see. We could have multiplied it by 100, but then we'd probably have buildings that were unbuildable. So we gave ourselves a little bit of extra load on there, but not too much. We were kind of very strategic about what we did there. In structures 2, we need to design and size the members. Sounds simple, right? Well, to do that, we have to bring all of those concepts together. We know what those internal loads were on that member. We now have to find what member with a reduced capacity is strong enough to support those loads. And depending on if it's steel and if it's wood or if it's concrete, the methods are slightly different on how to calculate that reduced capacity. And remember, we have to check axial loads, we have to check shear loads, and we have to check bending moment loads. So there's a few things that we're going to have to look at here. But by the end of it, we're going to have a perfectly sized member for our problem. Remember, perfectly sized means it is going to have a reduced capacity greater than the factored load. It is going to be stiff enough to not cause damage to finishes. It will obviously be stable because that was going to be problem 1 that we solved. And it is going to be the cheapest possible solution we can find. Remember, cheap is often related to weight or the amount of material within the object. So, number 1 goal, cheapest solution within our criteria that meets all of those requirements. So structural sizing guidelines, or our rules of thumb. Remember, it is key to remember that they're guidelines. They are not the designed solution, and they are mere suggestions. You can deviate from them, but we want to make sure you're showing something reasonable on your preliminary drawings. If you're designing a 5-story building, and on your project you draw beams that are this deep, you have a height restriction on your building and you've built right to the maximum height you possibly can. Your floor to floor height is pretty tight. You're just meeting the building code requirements for somebody to walk around in that building. You go to the engineer, you get that member sized, and you find out it's not that deep, it's actually this deep. And so now you have this amount times 5 that you have to add onto the height of your building. You're over your maximum building height, which means you have to chop a story off your building, and now the owner comes back to you and says, this building isn't financially feasible for me anymore. I needed to sell a certain amount of retail space to be able to make this project possible, so we have to scrap the whole project. It would have been very important to know that at a very early stage in the project, or come up with a framing solution that would allow your member sizes to be that shallow. So these sizing guidelines are usually come into play long before you have an engineer working on the project. So it's very important that you understand these sizing guidelines. They're about standard members in ideal conditions. They are not meant to be used for unique conditions. If you are supporting a gold smelting plant, these sizing guidelines are not going to be useful. If you are designing 54-meter spans, like gold ring, for example, these sizing guidelines are not going to be useful. You're going to find they're outside the realm. Those things are outside the realm of usual and not meant for the sizing guidelines. The sizing guidelines work two ways. If you know the depth, you can figure out an appropriate span for your member. So maybe you knew you could only have beams this deep because your framing was limited. Well, you can take that depth, multiply it by your sizing guideline, and figure out what an appropriate length is for that beam. And so now you know, I shouldn't have beams longer than this long in my project, or else I'm going to need to have a deeper beam to go along with that. If you know the span, you can figure out the appropriate depth. They will still be ruled by the final design. These are for very, very preliminary design. But lucky for you, the studio component of your project is a preliminary or schematic design set of structural drawings that you're producing. So the key is they will need to be stable. That is essential. You can't have an unstable system. But after that, you just have to make sure it is a preliminary sizing guideline that works on your project. We also looked at loads. Now we're going to go through some of this in depth next week. We figured out what the dead loads were on buildings, so that was the self-weight and also superimposed loads. We looked at live loads for people and stuff, and we remembered that over very large areas, it meant the probability of every single spot of that floor having that peak load on it got less and less and less and less. And so with that, we got to use a live load reduction factor. We talked about snow and wind being climatic design loads, and they were based on a 1 in 50 year probability of that snowstorm occurring. Are we finding that we're hitting those 1 in 50 year events quite often? Yeah, we are. We're in a unique situation where the climate is changing. Some of you might not agree with that. I'm not here to quibble with you. I'm here to tell you that statistically, we are seeing an increase in some of these loads. We looked at earthquake design. We didn't go too in-depth in earthquake. We looked at old school methods of doing earthquake design. So if you have the opportunity to talk to Pedram, they are going to say that they're going to have a very much more complex and in-depth way to do seismic design. We just kept it very simple for the components of our structural course, really to help you understand what's happening there, that really the ground's moving, the building's going along for the ride, and we took the weight of the building, how much force is acting on that building is very much dependent on its weight. If it's really short, it's usually pretty stiff and just bops along on the ground and not much happens. If it's really tall, it can sway quite a bit, and wind starts to be the thing that governs it. But there's this sweet spot range of buildings where earthquake is going to govern the design of the building. And for those, the way we used to do it, and we still do, but it's slightly more complex than that, we say that we relate the weight of the building as a percentage of its weight acting laterally on the building. So we, instead of saying the building is actually moving, we take that movement and turn it into, basically we take that acceleration and turn it into a force that's acting on the side of the building. So that's a pretty easy simplification of the problem. We looked at soil pressures, trying to push in on our foundation walls and fill that hole back in on us. We only briefly talked about temperature, pre-stress, and vibration. Okay, so today's lecture, we're going to go through strength, stiffness, and stability again. We did this last term. If I could, I'd do it as the last lecture again, simply because this is really where I try to let you know that everything you know about structures, you already know. Everything you need to know about structures, you already know. you already have a pretty good intuitive sense of how things behave for strength. Stiffness, you have a pretty good sense, and stability, you innately understand. I am going to show you how to draw, or I showed you last year how to draw stability. Remember, that was our free body diagrams. We talked about stiffness. Now, we didn't really talk about what was actually happening, how much these things actually moved, but we talked about stiffness criteria. We gave a limit on how much we'd let these things deflect. And we're going to talk about the difference between stability and stiffness. Stiffness is about how much we let things deform. Stability is making sure they don't move. So moving and deflecting are not the same thing. Movement, I've had to hide my foam block because my kids get into it and it goes missing. Movement means, is it flying up in the air? Is it sliding back and forth? And is it spinning around? We don't want those things to happen. If it is stable and it deflects, that is stiffness. So there's deflection or deformation and movement. We don't want it to move. We want it to be stable. And we have stiffness requirements or limits on how much we'll let it deform. Strength is life safety. So that's the amount of load a structure can sustain prior to failure. And this is about preserving life. So we want to know how much load the structure can sustain prior to failure. And then we try to make sure we build in a little bit of redundancy in the system. Because as I've said to you before, if I had this table here and we designed it exactly to support the weight of me and the self-weight of the table, and I went out and ate a cheeseburger and drank a beer and came back and sat on this table, I'd make this table collapse. And we do not want that to happen. Stiffness is the amount of force required to make a structure deflect by some fixed increment. So that does not mean our object is moving, it means it's deforming or deflecting. And stability, worst definition in the world, the state of being stable or the opposite of unstable. Instability can be elastic, ponding, tipping, or sliding. Basically, we don't want our object to move, and this is what you very much have an innate sense of. We have to check all three of these things for every connection, every element, and every system in our building. So strength, stiffness, stability get checked for every connection, every element, and every system. So like I said, this lecture is going to be pretty light, and for most of you, it's a bit of a redo. I'm in that brief window of time during the day between coffee and before wine. So coffee is from 4 a.m. until 10 or 11. Then I drink wine until 5 o'clock, and then we're into the evening at that point, and I'm off the clock. I mean, I just switch clocks. But okay, back in the day, we had a different way of doing our strength design. There were flaws with this process. It was causing us to sometimes not design the best buildings, and we were wasting a lot of material. We weren't being smart in our design process. So this system, what we said was, I'm sitting on my table, there's the weight of me, there's the weight of the table, we're going to add my weight and the table's weight, and then we're going to put some factor of safety on it. Maybe it's 2, maybe it's 5, depending on what application it was. We had a list of different things, and then we just had to make the weight of me and the weight of the table added up and then multiplied by some factor be less than the capacity of this table. The problem with that was the weight of me is much more likely to vary than the weight of the table is. The capacity of the table, though, also has some flaws in predicting it. There could be mistakes, not mistakes, but maybe there's a problem in just assigning the buffer into the load side of our equation. So what we did is we said, well, what if we do two different things, or two things different in this method? Let's reduce the capacity some amount, and let's treat all the materials differently. Let's give each material its reduction. So we're going to reduce the capacity of each material dependent on that material. And then we're still going to factor the loads on the system, but we're going to do it different. Rather than add all the loads up and apply a factor, we're going to say, let's look at each load type individually, because the odds of the table being wrong or having an increase in load is a lot less than me. I could go out and have 10 cheeseburgers and 10 beer and come back and sit on that table. I could, God forbid, have a third child and come back and sit on that table. So the variability in the live load is much greater than the variability of the dead load of the table. So what we do now is we apply a different factor to each load type and then add them up. We have factored up the load and reduced the capacity. We want that factored load to be less than the reduced capacity. Remember, we want the cheapest thing possible within our criteria. So if they're pretty darn close to equal, we have done a good job. We'll often use little symbols. You tend not to see the factored symbol or the alpha in front of load very often, but you will see this right here a lot in the coming term. If you see this, we are saying we have reduced the capacity. Now, engineers like to use Greek symbols for a lot of things. You're probably becoming more familiar with Greek letters throughout this pandemic. But if you see this, we're talking about a reduced capacity, or the amount we're reducing the capacity of that material. If you see the subscript F, you know that somebody has already factored that load. If you see the subscript R, you know that somebody has reduced the capacity of that member. They have calculated what its bending capacity is and reduced it just a little bit. So this is handy because now we know at a glance if we have to factor it or if it's already been done for us. So subscript F means it's been factored. Subscript R means it's a reduced capacity. So, for example, MF has to be less than MR. That is our goal. We have to do this for all the force types on our object. And the force types could be axial loads, shear, moment. Axial could be tension or compression. This is called limit states design. We break it up into two components. The strength side of it is the ultimate limit states design. And then in stiffness, we're going to talk about serviceability limit states design a little bit, or we did last year. So what are these force types that we talk about? Well, there is compression, and we squash things. Now, last term, we saw a lot of me using this wonderful object, and if I squash it this way, it really didn't do much to the foam, but this weird thing happened where it popped out sideways. And so that's something we're going to talk about a little bit later, and it's going to be very, very, very important in how we talk about design of materials coming up in the term. Tension is when you're stretching something. Shear. Now, shear force is difficult for people, I find. All right. Shear force is really what we're saying happens at each plane. These are my business cards, and I am saying that if I push down on this side and slide up on this side, I am talking about what happens on this plane. Well, then what if I go one business card over and I do the same thing? And I go over another business card and I do the same thing. And we do that again and again and again and again throughout that deck of cards. And we talk about that shear at each plane. Well, I could talk about it here and here. And I want to know what shear is happening kind of on that spread out distance. So we do that at infinitesimal kind of spots along the length of the beam. A lot of you probably recognize that as calculus. Now, we're not going to do much calculus. I'm not going to make you differentiate or do any integrals at all. But obviously there was a lot of that in my education. For us, we're going to stick to it being relatively simple, but I want you to notice something here. This was the original shape of our square. Look at the unique shape of this here. As we shear it, this side has come down and that side's gone up, and we've skewed our triangle. This distance is shorter than this distance now. So we've had a lengthening along this axis, or a tension along that axis, and a compression on that axis. And that is a pretty cool takeaway. It almost looks like we could convert shear some way into talking about tension and compression. Now, we're not going to focus on that, but it is handy in identifying shear failures. A lot of people get very confused about why a shear failure in concrete goes on a diagonal. Well, it's because we're pulling at a diagonal. When we do a shear force on something, it represents as a tension on the diagonal. And remember, concrete does not like tension at all. And we get a crack along that line. Bending. All right, we've got our handy foam block here. Bending is a force that acts to bend a component, putting one side of the part in tension and the opposite side in compression. You guys remember we did this using method of sections on a truss. And when we went through, we saw that the top chord was in compression and the bottom chord was in tension. And then we talked about how that could be represented as a moment. So let's look at it. Let's see if what I'm saying is true. If I bend this foam block, look at that. The top is squashed and the bottom is stretched. It does in fact look like the top chord is in compression and the bottom chord is in tension. And it almost looks like there's no change in the length of that pink line. It looks like not much is happening there. It's deformed, but it hasn't stretched or compressed at all. And all of those green lines, they all look like they've stayed straight, interestingly enough. And that's going to be really exciting and helping us in a couple weeks, I think in week 4, when we talk about stress and strain and how it relates to bending. So torsion isn't something we're really going to focus on in this course, but it's kind of a weird combination of bending and shear. So sometimes you'll even hear, if you've ever used an impact driver and overdriven or kind of twisted the head off, you know that you'll often say you sheared the head off of your bolt. So it's this action here. So we're not really going to get into that, but I just wanted to tell you that it exists. Connections are where elements meet each other. And so we can have brittle or ductile combinations of axial shear and bending and torsion on a local element. So if we have a beam connecting to a column, we have to connect them with something, and that has to be designed to handle the transfer of whatever forces need to get from this object to this object. All right, I find the best way to show images of compression, tension, shear, bending moment, stiffness, and stability is to find images that show failures. Showing you something that works doesn't really help you at all. Everything around us is meeting all of those requirements. The best way to show you what these things are is by visuals of them failing, of those things not working. Now, concrete has almost no capacity and tension. In fact, we will often say it has zero capacity and tension. Great in compression, so great that we use it all the time. But concrete has a flaw in that we don't really know how strong it's going to be until we actually make it. And we make it on site. Wood, we kind of make the elements off site. Steel, we make the elements off site. Concrete, we make in situ. We can try to predict what its strength will be. We can say what minimum strength we need it to be, but we can't be positive it was gotten right until we actually make it, but it's already being used. So what they do is when the truck comes to site and they pour their concrete slab or the columns or the beams, they also cast concrete cylinders. And then they take those 3 cylinders back to the shop, or the people doing the testing take them back. And at 7 days they test it, and at 28 days they test it, and at 56 days they test it. And then we see, did it meet the strength requirements we needed it to meet? I can tell you that it almost always meets it. And on the rare times where it hasn't, it usually required us to get very, very smart in refining the design of that element. Maybe we have to reinforce something, but very, very, very rarely do we say tear that thing down. I have seen it happen once or twice, but we will go through great lengths to make sure that doesn't happen. Sometimes we'll ask for extra fee, but we will do whatever we can to make sure that doesn't happen. Now look at this. Look at how this concrete popped out sideways. It didn't bow, it didn't buckle. So this is a true compression failure. We've been squashing this thing. But what really looks like it's happening is as we've squashed it, it's bowed out. And it's actually a surface tension failure on that concrete. It's interesting how almost everything we do comes back to a tension failure, interestingly enough. Okay, timber compression, similar thing. They look very similar to each other. These fibers have delaminated from each other and torn themselves apart. Strength failure. Steel's a really good one for this. We're actually going to watch the video that made this image later in the term. Now there's 2 things interesting here. There's this, which is what your eye is drawn to right away. This is a big takeaway. You think, okay, great, this solves all my problems and this is how I can see how it failed. But what's a really neat thing is if you measured this distance and you measured this distance, which was the same spot on the object, you would find that that is bigger than that distance. So something has happened. On its way to failing as a strength failure, there was deformation of some sort that happened equally along the length of this object. That's going to be really cool to talk about in 2 weeks' time. So I really like this image because it really helps clarify what a shear failure is. It's really easy to lose focus of shear in a long object, but in 2 elements slipping past each other, it is really easy to see that if we put a bolt through here and these slip past each other, we would somehow damage this bolt. If this bolt gave way, something would happen. Well, if I cut away these steel plates, we would see that the bolt goes like this, goes on a diagonal, and then across. So we have that diagonal failure of our bolt here. Well, look at this diagonal failure of our concrete. That is a concrete beam in shear. That is a failure of concrete in shear. Concrete has some serious flaws with shear in it. Now, we do things to help mitigate that. What we do in concrete is we put ties in along here. And it always messes people up how we put the steel in for shear reinforcing. Because you would think putting something right along here wouldn't help. But what we're trying to do is to prevent that from propagating. All right, a concrete wall in shear. So look at this failure. You can see we've got that classic diagonal failure because one floor was trying to shear past each other. Now I always like these 2 images side by side because it's pretty easy to see that this was likely a wind event. It could have been an earthquake event, but it was probably a wind event. And this was definitely a seismic event. A wind event is only going to happen in one direction. Now I know, I hear somebody saying, but what about tornadoes? Well, a tornado usually doesn't hit the entirety of the building all at once. And even if it did, those 2 forces usually counteract each other. Maybe if it was a giant tornado, you get it on one side, and for sure, you've got me there. You are right, that could possibly if it passed right across it, you could have gotten wind in one direction and then switched to wind in the other direction. Hurricane, same thing. But often even in hurricanes, the wind on one side of the hurricane isn't as high as on the other side. And it's not that immediate reversal. It's probably already failed from the wind on the first side. Earthquake events go back and forth very quickly with usually almost equal force, at least at the peak. It can have a really large impact in both directions. And so you can see that this one failed in both directions. Now, look at, again, the direction of these cracks. This is very similar to exactly what we do for braced bays. I'm going to see if I have, I meant to find it. My kids keep stealing all of my cool supplies. I bought something specifically to address these things. What did they do with it? Okay, well, I'll find it and I'll have it in time to talk about what we need to talk about coming up. But I bought something to build a little braced frame for you guys. Dang it! It was hard to resist for them, I can imagine, because it's actually a tool. There's a chance that Dave didn't even realize what it was for and gave it to them. All right. Well, I can even build a new one. I have the set of the toy so that I can rebuild a new one. But that line is exactly the line of our diagonal members in braced bays. Now, there's variations to those. As you guys remember, there's all kinds of variations we can do. But that's usually the cheapest primary format that we do. All right, bending failure. So this is a wood beam with a load bending downwards. So the top is in compression and the bottom is in tension. And you can see that this wood split right here and we have a bending failure. I didn't list it, but there's also a crushing failure right here. So our wood kind of crushed a little bit right where the point load happened on it. Remember how we've talked about pin roller conditions? When modeling this, you can see that they've built in literal rollers into modeling this. Okay, a concrete beam in a bending failure. So this one isn't a shear failure, it's a bending failure. Now this one is bending upwards. These are not the supports, those are the load applications. So this beam is much longer than what we're seeing, and it's supported at the ends here, and it's being bent upwards. So tension on the top, compression on the bottom. Concrete is crap in tension. So you can see all of these tension cracks. Now what we do to stop these from propagating is we put reinforcing in here. Now normally our beams are bending in the opposite direction. But look, there was even some crushing of the concrete right here. Steel. Steel has a wonderful, unique property that we make use of called ductility. We're going to spend a lot of time talking about ductility. What I've always said before is that strength, stiffness, and stability are very distinct things, but it's not always obvious how distinct they are because they can turn into each other very easily. So this steel beam had a load being applied to it like that. At some point, it yielded here. We're going to talk about what yielding means going forward in the term. So it yielded here, and then we got large amounts of deformation. It hasn't broken through like our concrete and our wood did, but it is bending so much that we have exceeded any stiffness requirements we might have had. And look at this, it bent so much that if that was on supports, they would have come right off their supports and turned into a stability problem. So we can see situations where it's not always obvious which thing precipitated which. And we're going to talk about those a little bit. And part of your assignment problem, and it's literally the same assignment you did last year, so don't panic. Some of it is I want you to think and talk about it. Have a discussion during the tutorial if you'd like. Because some of these things, some of the ones I gave you in the assignment are a thought exercise. And it might not be obvious which one is the right answer. And there might be multiple right answers for some of them. So here's a steel bolt in a torsion failure. You can see I said it's kind of a weird combination of bending and shear. Look, you can see it's got that diagonal failure similar to what we see in shear. Here's torsion in some sort of drilling shaft. All right, here's some connection failures. I usually take this one out. I don't like this one that much because it's not exactly clear what's happened here. So I'm going to skip this one. All right, what I do like is this image. These are two different, these weren't in the same thing. I think it's just two sides of the same screw. But you can see that this was where two things slipped past each other right around here, and it has deformed this screw in that diagonal shape. This is a clear indication of a shear failure. Here's one where you can see that bolts sheared right here. Now, this doesn't mean that the actual design for this was under-designed. Sometimes what happens in construction is, if you think about it, the expensive thing during steel construction is the crane. Getting that steel put into place is dangerous and time-intensive, and it stops all other construction on the site quite often. So it's very expensive to install the steel. So what they'll often do is to speed up the steel installation, they'll have someone follow around and only put 1 or 2 bolts in to make it stable while they install the rest of the steel. And then they come back and usually hire the cheapest person on the site to go back and finish putting all the bolts through, when they're not paying the very expensive crane operator to be waiting while they install the bolts. What sometimes happens by mistake is that the rest of the building gets built without those bolts getting put in. So when I do a site review for steel, one of the main things I'm looking for is are all of those bolts installed. Here's a plate in tension. So this plate was actually pulled apart. All right, I like this one because it really talks about our intuition in structures. Okay, if you have a friend around, stand up and get them to keep your feet together. Actually, stand on your tippy toes. Keep your feet together and get them to push you forward. You'd tip right over. If you put your feet on the ground and hold your ankles rigid, you'd do a little bit better. Now, if you got them to push you sideways, what could you do to stop them from pushing you over? And you know that what you would do is you would widen your stance. Intuitively, you know to deal with that load that's coming up high on your body, you would separate or widen your stance to stop you from tipping over. What you've done is created a couple. So a load is up off the ground, so that means a moment is being applied to you, and your place to resist it is at the ground. Your feet aren't moment connected to the ground, so instead of a moment connection, you turn your feet into a couple. One side's trying to lift up and one side's pushing down, and the act of that resolves our couple. What happened here is there was moment on this column, but the couple of these two bolts was too close together, so it didn't really help. If what we were going to do was try to solve that, is we would spread those anchors out apart from each other. Maybe they need to be really far apart. Maybe this shouldn't try to be a moment connection. Maybe there should be a lateral load resisting system somewhere else in the building. We don't know what this exact condition was. This is trying to find a backstory for what happened based on internet pictures. Okay, I've provided for you some videos of things failing. Feel free to watch them. I would normally, if we were in person, play these up on the big screen, but I find if I play videos while I'm recording, it creates this weird lag, and any noise you hear from me makes weird sounds in the video. So I will let you watch these on your own. There's 1 or 2 videos that I will definitely watch with you in the lectures throughout the term, but these ones are more just for you to be able to take a look and enjoy yourself. This one's actually embedded in the lecture. I really like this one because it shows a few different failure types. While I was working with Cast Connects, they have the unique opportunity to do things that most structural engineers don't get to do, and that is test real size objects. Engineers mostly test little bits of things, if we even test things. Mostly we're just provided data from someone else doing all of those tests, and then with that data, we design large scale objects. Because Cast Connects was creating new steel objects, and they needed to be able to prove to building departments that they could represent those things as calculations, they needed to do calculations, but then test real size objects to prove that their calculations matched these tests. So their object is this right here. It's one of their high strength connectors, and it's welded onto a steel HSS column, and it's connected to a plate. So this would have been used to help with seismic loads on a building. It builds in a little bit of ductility. Now, ductility is when we have large scale movement. This is all stuff we're going to talk about later in the term. I just like this video because it starts to give you a taste of what we're going to do. This diagram here is also something that we're going to be talking about later in the term. It plots force time against movement, or stress times strain, or versus strain. We call those stress strain diagrams. Now, one where we load it and unload it and load it and unload it, or load it and then load it backwards even, we call a hysteresis. So this is what happens in seismic loads. Because we have that back and forth movement, it gets loaded and goes through a cycle, and then we test it again. And that is a hysteresis. So what you see mapped out here is a hysteresis from a seismic loading event on a steel column with a high strength connector. You're going to see bending of the plate, you're going to see local failure of a column wall, and overall buckling of the column. This is another video of a Cast Connects product. This is back when they've totally revamped this now, but when I was starting working with them, they called this their Scorpion. They've since changed the name a little bit because they've come up with kind of a cheaper way to build this thing. What I really like about Carlos and Mike is they're both U of T graduates. One has his PhD, one did his master's. They did it in castings and steel, and they've taken their engineering knowledge and they've also created a lot of architectural elements, which is fantastic. So this is another cyclical loading event, and the idea here is that all of these fingers start to resist the load, and because they're triangular in shape, they really make maximum use of the steel material in resisting the loads. So there's lots of cool stuff going on in this video, but it's also really fun to watch stuff fail. So feel free to watch that video too. Okay, let's move into stiffness. So that was all strength. Let's talk about stiffness now. Okay. Stiffness, we have stiffness criteria. It's not about life safety. This is usually about preservation of finishes and human comfort. We're going to talk about what goes into kind of defining the criteria in the next slide. So we're worried about vertical stiffness, horizontal stiffness, vertical stiffness, rotational stiffness, soil stiffness, and vibration. Now, some engineers would argue that vibration doesn't really fit in with the stiffness criteria, but in terms of talking to architects, I find it easiest to lump vibration in with stiffness. Okay, now don't worry about this too much, but I just wanted to let you know that you understand the term stiffness. Most people understand flexibility. Well, stiffness is just the opposite or the inverse of flexibility. If something is very flexible, it's not stiff. If it is not flexible, it's very stiff. So what sets our stiffness guidelines? Well, human comfort. Are we comfortable with whatever is happening? People don't like standing on a floor that bows, or if they walk across it and feel it drop while their load is on it and they come back up. Preservation of finishes is a big one. We don't want to see cracks in our ceiling. We don't want our windows to bust. Stability can set stiffness guidelines. Something might need to be stiff enough that it doesn't turn into a stability problem. And we'll talk about that. And it can be tied in with drainage as well. And then interface with building elements. So how two things might deform relative to each other. So some of the little bit of math that you're going to have to do in this week's assignment, which again is the exact same as last term, is about serviceability limits, or the serviceability limit states design. Sometimes you'll see me call it SLS versus ULS, which I use for strength. So this is a very quick overview of the guidelines. Now, this was updated last year, I'd say, just before I started teaching you guys. Some of these criteria have changed throughout the codes, and these are based on the individual material codes. Now, some of them no longer publish explicit standards, but the industry has standards that even though they're not published, you still probably want to meet them. Serviceability is not a requirement in the building code. It is a very, very, very strong suggestion in the building code. So much so that I would say probably 90% of the lawsuits you see in kind of architecture and engineering components is about stiffness. It is about damaged finishes. It's very rarely about strength because there's very few actual failures in things. I just remembered there was a shear diagram, a shear image that didn't put in these slides for shear concrete because it was a really good image of punching shear. Anyway, so these stiffness and serviceability limits are a very strong guideline. I would always try to meet them. There would have to be a very good reason for me not to meet them. If I'm not meeting them, I need the architect to understand. And if we're not meeting them, the architect and I need to make the owner understand. So for example, that Sisters of St. Joseph canopy that I designed met all of the strength requirements, but it was going to have to look very chunky to meet the serviceability requirements. I talked to Bridget and Howard and I said, here's what happens under a 1 in 50 year snowstorm. If we're comfortable with that, here's what happens in a 1 in 10 year snowstorm. And then here's what happens on an average snowstorm throughout the year. And everybody agreed, because there was no finishes that could be damaged, it was just the steel itself, everyone agreed we were comfortable with those possible movements in the structure, and it got built without following the serviceability criteria. But there was real steps taken to make that happen. Okay, so what information is in this? Well, whether it's a roof or a floor can change the criteria. Whether it's snow by itself or dead and snow in combination, or live by itself and dead and live in combination. If you had a roof that had access to people, you'd worry about snow, you'd worry about live, and you'd worry about dead and snow together and dead and live together. You would not have to combine you would not have to combine the snow and the live. And then we have the finishes. Is it susceptible to damage or not susceptible to damage? I'm going to tell you right now, drywall is susceptible to damage. So drywall, sometimes called gypsum wallboard, sometimes called GWB or gypsum wallboard, GWB, that is susceptible to finishes. If you see those terms, please know I want you to follow the guidelines for susceptible to damages. Okay, and then, is it steel, wood, concrete, or masonry? Masonry has some of the tightest guidelines. Concrete has a high one as well, L divided by 480, but masonry also has a hard upper limit of about 3/4 of an inch or 20 millimeters. And that's because masonry reads cracks so easily. People get wildly mad with cracks in their masonry, and you're all used to seeing masonry or block with cracks along those mortar joints. Okay, so this makes great exam questions. I guarantee there will be probably 2 of these on the exam simply because they're easy to make and they're easy points if you just read the question. Okay. If we are so what we're saying is we have the length of the beam and we are given a serviceability limit, and we're saying that's the maximum deflection we're allowed to see. So this is our Greek letter delta. Delta means change. Don't get it confused with the COVID variant. This is delta means change, or how much deformation we are allowed to have in this beam. If it's a cantilever, we can do 2 things to help us get our head around it. We can ignore back here, we say, okay, this is the length of our cantilever, and we can take our deflection criteria and divide it by 2. Or you could say, if this is our cantilever, it's the same thing as a beam that's this long, meeting our normal deflection criteria. Or we could double the length of our cantilever and divide it by the normal deflection criteria. I normally treat it, it's the same information. This is the same thing. It's 2 different ways to say the same thing. What you'll see me do usually is just take the length of the cantilever and divide it by 2. But I like to show you this because it explains where that's coming from. Okay, stiffness serviceability limits. Let's do an example. What is the amount of live deflection we will accept for a wood floor beam with drywall? So the drywall tells it it's susceptible to damage, that spans 10 feet and has a 2-foot cantilever. So here's our cantilever and here's our back span. Okay, so we've got live load. We know what load type we're caring about. We know that it's wood. We know that it's a floor. And we know that it is susceptible to damages. So let's look at what our criteria is. All right, so it was a floor, live load, susceptible to damages, and it's wood. So it looks like L divided by 360 is the criteria we're going to use. So let's convert our 10 feet into meters or millimeters, because I usually like these answers in millimeters. Again, in the assignments, you will see very explicitly how many decimal places to put and what information I'm looking for. Okay, so let's take our 10 feet, multiply it by 12 because there are 12 inches in a foot, times 25.4 because there are 25.4 millimeters in an inch. I end up with 3,048 millimeters. My live load deflection criteria for a wood floor with finishes is L divided by 360. So my allowable deflection, or the maximum deflection I would allow this beam to see, is 3,048 divided by 360, or 8.47 millimeters. Let's talk about our cantilever here. Okay, so our cantilever is 2 feet long, or 610 millimeters. We know that the wood floor with finishes supporting live load is L divided by 360. So for a cantilever, it's L divided by 180. So my allowable maximum deflection for the cantilever is 610 millimeters divided by 180, or 3.4 millimeters. So you can imagine if we put a big point load right here, we're going to deflect down like that. We might actually pop up here. But if we put a big point load here, this could deflect down and pop up here. Or we could put a load all the way across this uniformly. And we don't know, is it going to go down there and bend up a little bit? Is it going to be so heavy that it's going to bend down and bend down? We're not quite sure. That's why engineers really look carefully at a cantilever deflection that doesn't meet serviceability criteria. Because sometimes if it's very short, our criteria says we can have 0.01 millimeters of deflection, which is just crazy because that's totally fine. And so sometimes we might say, okay, let's take away this criteria because it's not reasonable. All right, serviceability limits for lateral loads. We have 2 different criteria we have to meet for 2 different load types. We have wind that's trying to tip our building over, and seismic loads. Now there's also live loads and other things that we have to worry about, but usually these are the ones that are going to be the problem here. Our deflection criteria for wind is H divided by 500, and for earthquake it can be H divided by 50 or H divided by 100. And in some places in the States, it's actually H divided by 40. So there's variability in what that criteria is. Let's say I had a 32-story building with 3-meter floor-to-floor height. Let's say 4-meter floor-to-floor heights. So 32 times 4, let's times it by 1,000. I have 128,000 millimeters tall divided by 500. I'm allowed to move my building at the top 256 millimeters, or 10 inches. That is a huge amount of movement. Luckily, many steel buildings are very ductile, and we can allow those sort of movements. In fact, it can actually help us for some things. Seismic loads, we can end up with huge deformations, really, really large deformations. Now, that's the height of the building as a whole. We also have the criteria that any single story needs to meet that criteria, so that we don't end up with a really stiff building where all of that movement comes out in one story. All right, vibration. I know I've lumped it in here with stiffness, but I want to talk about a few things about vibration. Now, I did this with you guys last year, but stand up, and the human body tends to move at about 2.5 hertz. All right, now go up and down on your toes as slow as you can. You feel that burn pretty quickly. Now I say, go up and down as fast as you can. It starts to burn. Now, do it at the pace that's the most comfortable. This is the pace I could do it for a really long time for me. What's really interesting is when we're all in a room together, everybody's moving at different times, but the rate of movement tends to be almost the same. And it's going to be pretty darn close to 2.5 hertz. And we have that cyclical movement. So we are very sensitive to a movement of around 2.5 hertz. I always like to keep standing up for this. All right. We are very sensitive to transient vibrations as well. If we feel an impact load of some sort, we care about how quickly it disappears. If somebody drops something on the floor beside you and you notice it, that's fine. It goes with the loud bang and you feel the movement and then it disappears. You tend to be okay with it. But it really bothers you if it keeps going. So I always do a nice big heel drop. You're going to see my camera move. Now, what's interesting about that, you probably noticed that my window rattled longer than the camera kept moving. My camera is on an arm stand that is actually dampening the load that my window didn't have the benefit of. So my window vibrated longer because it was more susceptible to the transient load. One of the other ways we deal with transient loads is by mass. So most buildings have a concrete topping on the floor, even if they aren't built with concrete, because we like concrete to deal with dampening our load. Now, I am not a huge fan of concrete construction and what it does to our environment, and there's a lot of talk about that. The one place I do feel it solves a large problem is on toppings for floors. Now, there are other methods of doing it, but if you're already pushing innovation in a lot of spots, using your concrete smartly becomes a very good thing to do. So if we can get rid of 90% of the concrete construction and limit it to a much smaller portion, we're doing a good job there. Should we eventually get rid of all of it? Probably, but using it smartly is the best thing we can do right now. All right, amplification or resonance. That's when two things respond, or when an object has the same vibration at a natural frequency as the load being applied to it. So if a bridge, for example, has the same natural frequency of, say, 2.5 hertz, and a group of people are marching in lockstep across the bridge, it could cause amplification. In fact, you've probably all heard the story of a bridge actually, a pedestrian bridge actually collapsing due to an army movement of everybody walking across in lockstep. Now, there's debate about the truth to that rumor, but for a very long time, armies did tell marching teams that they could not march in lockstep across bridges, simply because it was very dangerous for the bridge. So it could also be wind or seismic loads. We need to make sure the natural frequency of our objects does not match the frequency that is going to apply the load to our object. Vertical deformation. So a beam in bending. What kind of, I wish I had something long and flat. So how much deflection is that, or deformation? So not movement, because my object is staying still. You might hear me say movement sometimes. I'll try not to, but I'm talking about deformation. So this was my old crappy house. And when Dave and I moved in, we threw everything we owned up in the attic on a floor that wasn't even a floor. It was literally just rafters. So we put wood down up there and threw all our storage up there, with the understanding that there was a beam in here for this little pop out. When we decided to do our renovations, when we took the siding down, we saw that what was in here was just a 2x4 on flat. It had about 2 inches of deformation in its span, and I think that was about 8 feet. So 8 times 12 times 25.4. Let's say it was all live load, so divided by 360. We should have been allowed, the maximum allowable deflection for that beam should have been 6.4 millimeters or 6.8 millimeters, or around 1/4 of an inch. So 1/4 of an inch. It had deformed 2 inches. So obviously the beam that was there was undersized. Forget about strength. Like, it obviously didn't work for strength either. It hadn't failed, which tells us that there's lots of redundant load paths in wood construction. But we very much needed to solve this problem. So we did the calculation. It ended up being 3, I can't remember if it was 3 2x8s or 3 2x10s that we needed to put in there. So we had to jack the floor up and then put the new beam in. All right, here are some cracked finishes. This is a failure of deformation. And you can see once it cracks, it can propagate all the way across. So even though your problem's here, it can result in a propagation of problems. Differential settlement. So soil, if you put a heavy load here, you can end up with differential settlement between 2 parts of soil. And like I said, masonry really telegraphs a crack easily. So most materials, you might get a little crack here and a little crack here and a little crack here and a little crack here. Masonry, all of your deformation will happen in one spot and it will read as a gigantic crack. Here is a block wall that I'm assuming is unreinforced, and there is soil trying to push that wall in. Here is why we need lateral load resisting systems. So this is a building that has a big opening in it, and these pieces of wood probably were not connected together in a way to transfer loads across the shear plane on how they relate to each other, meaning that under a lateral load, our building collapsed. This is a common thing you see in boathouses, for example. Okay, I'm not going to play the videos. You can watch this video, but I really love this video. A, because everybody just stays calm while an earthquake hits this gigantic building. So this is a tune mass dampener. It's a big, heavy weight that's supposed to help offset the movement at the top of the building. Think of it as a glass full, a glass full of water. When it's pushed, if it was empty, it would slide. You fill it with water and you push it. The water moves, sloshes around, and ends up actually stopping the cup from moving because the water moves really fast, hits the far wall, comes back, so it tries to, as much as the cup's moving forward, the weight of the water is moving backwards, and it stops the cup from moving. That is a very simplified method of talking about a tune mass dampener. This one, I need to point out that the camera is mounted to the building. So remember, the building is what's moving, but it doesn't look like the building's moving because the camera is on the building. So you can't see that the building's moving. What you can see is the damper moving, and you can see the people trying to balance themselves. I always find it interesting when people say, why aren't 100% of live loads counted in seismic disorder? Or why don't we use live loads to add to our seismic load that's applied to the side of the building? Because people are natural dampers. We automatically try to throw our weight to the opposite side the same way the water does. So you could say that maybe if your building was full of people, you could actually limit the effect of the earthquake. But what are the odds of that? We have to assume that it's barely occupied, and those people that are in there need to get out alive. So the worst case load is no live load, acting as part of the lateral load. We do say that there might be live load downward though. So we kind of massage things a little bit there. What's really cool about this video is one person is getting their picture taken during this earthquake, and they wrap their arms around the side. All of a sudden, they stop moving around, and they look like they're staying still because now they're moving with the building and the camera. I have two more cool videos for you to watch. These are both amplification. I'm assuming the football stand collapse is amplification. It looked like it to me. So this one is a bunch of football fans getting very excited and yelling and screaming. They start stamping on the floor and it collapses. I don't believe anyone was hurt. The Tacoma Bridge collapse is a very dramatic version of amplification. Now, it's not as simple as that. There was also resonance of the cables and how the bridge deck moved. So the Tacoma Bridge collapse is much more complex than simply saying amplification, but it's good enough for now to try to lump it in with amplification. It is a wind load acting on the side that starts to make the bridge deck sway. There was one loss of life, unfortunately, in this, and that was the dog that was inside of the car while it was happening. Don't think they didn't try to save the dog. An attempt was made to rescue the dog, but it was so scared it bit the owner, and the owner needed to get off the bridge, and the bridge eventually did collapse. So watch those videos. They're really interesting. Okay, stability. Stability, I think, is the one you most intuitively know, but the second I make you draw a free body diagram, it's like it, poof, disappears from your head. You stop thinking about stability. Now, if it's stable, it's not moving up and down, it's not moving back and forth, and it's not spinning in space. And no part of it is doing those things. So it's not about just it. No part of it is doing that. So my pen standing upright like this, tipping over, that part of it is spinning in space. Even though the bottom isn't, well, I guess even the bottom, it's spinning about that point. So we need to make sure it has restraint in this direction, and in rotation. We need to, in a 2D plane, ensure there is restraint in 3 degrees of freedom. In real life, we have 6 degrees of freedom that we need to restrain, but it's a lot easier to break things down into a 2D plane. I'm getting lots of emails. from daycare. I'm about to find out if my youngest gets to go to daycare next week. They were understaffed because so many people were sick. And then a meeting I am missing right now. 2 of the architects have COVID. So if you want to know what it's like to be a mom of small kids during COVID, there are lots of tears and there are lots of anxieties. I know I'm kind of diverting for a moment, but I think it's really important to, when the opportunity arises, to address things, because you guys are not going to be working in isolation your whole life. You're going to be going out there in the world, and it's easy to think that the things that cause you stress right now are magically going to disappear when you're done being a student. I don't know if it's easier or harder. I can't put my finger on it if life gets easier or harder. Sometimes you feel like you have more answers, and sometimes you feel like you have less. But I can definitely tell you that being a mom during COVID, especially a mom of small children, is it is a daily struggle in managing anxiety, managing a household, managing workload, managing relationships, because you have no help, you have friends, but all of a sudden the only way you can communicate with your friends is more online time, so I'm not trying to belittle anything you guys are going to, because I cannot even imagine how hard it is to be a student right now. It's got to be absolutely bonkers. So I'll try to be very understanding of you guys as well, if hopefully you'll be understanding of me. Okay, let's go back to our 2D problem with 3 degrees of freedom, meaning we have 3 lovely equations to help prove we have stability. But before we do that, we just need to even draw a free body diagram. I'm not even going to draw these right now, but we'll talk about what needed to happen to keep those things still. So some of the things we worry about with stability is sliding, tipping, elastic, ponding, no load path. No load path means we did not have a free body diagram that worked from the beginning. And buckling. Remember that funny thing we talked about? If I tried to squash this way, no problem, I'm squashing my phone. I try to squash this way, the whole thing pops out sideways. So there's something beyond strength there that's happening, and that's buckling. Okay, so don't worry about the arrows in this too much, but sliding is when the force that's pushing sideways on our object there is not enough friction to resist that load. So our object slides. So don't worry about the arrows. I don't even want to think about that. But we didn't have enough resistance here, so our object slid. Tipping, maybe we have a ton of friction resistance here, but we don't have enough weight to hold it down to resist the moment. So our building tips over this point. Elastic stability. So you can imagine in a world where I've designed this beautiful straight column, but some small amount of deformation is built into it. Maybe it was built a little crooked, maybe it was built out of plumb. And so our load that was meant to come straight down through the column is now not acting directly through the middle of the column. It is now causing a slight eccentricity. Remember, moment is force times distance, and if we have eccentricity from the center that we wanted it to be on, we've got moment. So we've got some eccentricity here pushing downwards. Well, that causes it to move a little bit more, which now we've got more eccentricity, so we have to check it again and see how much it moves. And we do that check again and again and again, and if the amount it moves decreases with each check, we've got a stable system. If that amount increases with each check, we've got a problem. You'll often hear that called P delta, or our force deformation problem. As we apply that load, we amplify our deformation or our deflection. It's really apparent in ponding. So I'll show you a picture of this. But you can imagine that if we have water on a roof and our building or our beam deforms right to here, more of the water is going to pool in right here. We're going to have a higher amount of water right here at the middle, right where the worst part of our beam is. So it's going to cause it, more water there means there's more load in the middle, which means our beam's going to deform a little bit more, which attracts a little bit more water. And so we do that check a few times, and if that increment decreases, you can see that this increment was smaller than this increment, we have a stable system. We still have to make sure it's strong enough. That's a separate check. We have to make sure it's strong enough. We also have to make sure it's stiff enough. Has this process deformed or damaged any of our finishes? So making sure it's stable is step one. Then we have to make sure it's stiff enough, and we have to make sure it's strong enough. If that increment increases, it's unstable. Buckling. So I have my compressive load on it, and it tries to pop out sideways. That is buckling. Local buckling is basically when one element of our object buckles. So instead of the whole thing buckling from a compressive load, if this, for example, was a beam, and we have our top chord and our bottom chord. Remember, if it was a normal beam and normal bending, the top chord is in compression. Well, if just the flange buckles like that, I'm not as good a drawer as my husband, if just the top flange buckles, or a portion of the top flange buckles, that's local buckling. Oh, I didn't include lateral torsional buckling. Well, we'll show that when it comes to it. I have a picture of that. Okay, let's look at pictures of stability failures. It's not always easy to tell if the failure is actually stability or not, but I have some pretty good pictures that I think capture a lot of it. So this, I can't recall if there was any loss of life with this. This happened while I was working. Like, I remember this story. It was a big deal when it happened. This wasn't an occupied building. It was in a construction site. So it wasn't fully occupied, thank goodness. And this occurred because it was a construction site. So on one side of this building, there was a big hole dug, and they took all of that soil and put it on the other side of the building. So if you guys remember, dig a hole, everything wants to go into it. Put a big weight beside that hole, and that's your surcharge. It really makes all the soil want to go into that hole. And then it rained, like flooding rain. So you can imagine that it became very easy for that soil to move and the building to just tip over. A lot of people comment about how these little foundations wouldn't have been enough to hold up this building. They probably were. They were probably just fine to hold up that building for its compressive load. It was not meant to have that loading condition on the soil. Sliding. It is really hard to find a sliding failure picture. I am not sure how this building got here. I can't quite figure out if it was a flooding event, but I've been in spots after a flood, and the soil doesn't look like this, and this looks relatively recent. It doesn't look to have been a tornado because the trees all look fine, and it's near a power line. You would think it would have brought down the power line. I wonder often if it was on a flatbed truck, but normally it's not completely finished like this. It almost even looks like there's curtains in the windows when they transport it on the flatbed truck. So I have never been able to determine what caused this photo. All right, I like this one because this one really talks about the ponding problem. Ponding is a real issue for buildings that we retrofit with new air conditioners, for example, new mechanical units. As our requirements for environmental processes in a building increase, especially with COVID, with all of the new air filtration systems we're required to have, you can imagine we have this roof that was designed for its loads, it was designed for strength, it was sloped to drain, and it met all of its stiffness requirements. Fantastic. We take this mechanical unit, we bring it and we plop it on the roof. There is a desire to check and see if that roof can support the load of the mechanical unit and the snow that builds up around it, and see if it works for strength and see if it works for stiffness, and to walk away from the problem. But what we have to remember is that increased weight changes the permanent deformed shape of that roof. It is now going to be a lower point than it originally was. If it causes the water to not slope to the drain anymore, we can have water pool around that mechanical unit. Now, that water is an additional weight, so it's going to deflect a little bit more, which means a little more water is going to pond there, until the addition of this unit that worked for strength, that worked for deflection, causes a ponding instability problem. All right, I said I didn't explain lateral torsional buckling. Well, our column that buckles sideways under compression, in our beams like this, remember the top chord's going to be in compression and the bottom chord's going to be in tension. Look what happens. The top that's in compression tries to buckle. The bottom is in tension. It doesn't care about buckling. It's going to do just great. Because only one side is buckling now, it tries to twist the beam. And that is why we call a buckling failure of the top chord lateral torsional buckling failures. It tries, as it buckles sideways, it puts the weight off of the center of the beam and causes the whole beam to twist. All right, here's a buckling failure of a steel column. Buckling sideways. Now this one happened to have a moment connection top and bottom, so it's still buckling, but it's a slightly different look to it. I'm going to come back to this one in just a second. Oh no, it's way further down. Never mind. Okay. I show this same image with local buckling because I find people also often get confused about what local buckling is versus buckling. So local buckling, I show this same column setup with the addition that one side of it is really buckled. Okay, when I was installing that wood beam up here, you can see that there's a jack post here, but this is only good for large increments and changes. We needed the wood jack to do small incremental changes and then keep moving the pin up on this. What we noticed is that one 2x4 didn't cut it. It wanted to buckle. So we laminated two 2x4s together. So we made a 2-ply 2x4, a built-up column out of wood. And then we put it back on the car jack and kept pumping it up. We got to the point that we had the post in, but our column, our built-up column, was really close to buckling. So for fun, we decided to take it to the point that it would buckle. We knew our beam was fine because it was going to come back down on this post. So I myself kept pushing on this car jack until I manually managed to buckle a 2-ply 2x4 built-up column. And we're going to do calculations about that later in the term. If anyone has taken the GO train a lot in their life, which I used to commute a lot by the GO train, if anybody has had the train delayed, yeah, it gets delayed when it's really cold, but it gets delayed more due to heat. The rails want to expand, and they're held in place by these rail spikes. If it gets really hot, these want to pop out really easily. So they make the train go at a reduced rate in the heat to prevent these rail spikes from buckling and deforming the tracks. All right, here is local buckling of a top chord flange of a beam. Remember, compression is what causes buckling, and the top flange of that beam is in compression, so it's trying to buckle. Here's another local buckling failure of a top chord. Here's that same steel column where you can see that there is local buckling. So this is what's really cool. It started to buckle sideways, and now you can see that the inside of this isn't just taking the compressive load, But now it's like it's bending sideways. So this is in tension, and this is even in more compression. And so that inside face of it locally buckled. Here's just a thin steel silo buckling. Okay, so here is what you need to do all the time. Is it strong enough? And by strong enough, I mean, is it strong enough to resist? Is the reduced capacity greater than the factored load for moment shear, axial, and torsion? And axial can be compression or tension. Is it stiff enough? And is it stable? You have to ask yourself that for the entire building and every system in the building, the elements, every element, and the connection, every connection. So, is it strong enough, stiff enough, and stable? And we're doing that for every system, every element, and every connection in our building. So, you can imagine that we go through this check again and again and again and again. We get pretty good at knowing the stable version, and then I'm going to teach you the calculations for stiff enough and strong enough. Last term, we figured out how to calculate the factored loads. So now we just need to figure out the reduced capacities and make sure that the reduced capacity is greater than the factored load. And last term, and we just did it again, we looked at the allowable deflection. So we know how much we'll allow it to deform. Now we need to figure out how much it actually deforms and make sure that actual deflection is less than the allowable deflection. And so if we can do all of those things, we will know we have an element that works. So what are your takeaway tips? I usually like to break the takeaway tips into two components. One that is forever tips that forget my class, that's not always the most important thing. Some of it is the fact that you're about to go out into the world and be a practicing architect, possibly. And the things you need to know to pass my course might not be the same thing. Maybe there's something I can't test you on, or maybe it's something that's just helpful that you understand and know. Sometimes they are the same thing. They might be, they might not be. Huh. Sorry, there was just someone in our driveway and I was just checking to see what was happening. I'm assuming it's a mail delivery, but it's not an Amazon truck. It's not Purelator or anything like that. So I was just confused about what was happening. So there are forever tips and the things to pass the course. A lot of times they'll be the same thing, but not always. So for both things, you should understand the different types of strength failures. You should be able to recognize a stiffness issue, and you should be able to recognize a stability issue. Within my course, you should also be able to calculate, I know what it is, I'm doing a Scotch. Sorry about that, I was about 2 sentences away from done, and that wasn't a mail delivery. We're doing a virtual Scotch tasting on Friday night, and so they were just dropping the Scotch off for us. So I certainly didn't want to miss that delivery. So you need to be able to recognize stiffness issues, stability issues. You should be able to calculate factor of safety and limit state designs equations, and you should be able to calculate allowable deflections. They're pretty simple equations. Remember, factor of safety, you just multiply the sum of all the forces by some factor of safety, and it has to be less than the capacity. We don't like that way. We don't do it anymore. Now we make sure the reduced capacity is greater than the factored load. And allowable deflections, we did an example of that, and so you can look it up on the chart and see what you need to do there. So next week is going to be, you might see my face, I'm not sure. It's almost all calculations. In fact, it's just a calculation review from last year. Those answers are already posted, so you can look at those. I have to make the assignment for that because it's a new lecture that I haven't done before. So I'm going to go through those problem sets that are posted just so the people that have never done it can hear the terminology and see what's happening and kind of get used to what we're expected to do, because that part of it we're going to start doing very quickly throughout the term. In fact, we're going to do some examples throughout the term where we just breeze through that because we're expected to already know that. So this was great, and I'll see you guys next week.